some sense, you know, everything in the course up to this point has been leading to this lecture. Okay, we're going to finally find out how, if you drop your robot or agent into some unknown environment and you don't tell it anything about how that environment works, how can it figure out the right thing to do? How can it maximize its reward in that environment? How can it figure out the actions that lead to the most possible future reward without telling it anything in advance about how this environment works? So that's the goal of this class, model-free control. And after we've seen this class, in the subsequent lectures, we'll look at how to scale up, how to get to more realistic, large-scale domains. But the core techniques are essentially building on what we saw in the last lecture and bringing those into a control setting now. So roughly the proceedings for today, we'll have a brief introduction. And then what we're going to look at is two different paradigms for doing control, on policy and off policy, which will understand the distinction between those. Essentially, on policy means learning sort of on the job, whilst you're following the behavior that you're learning about, and off policy means learning whilst following someone else's behavior. And so we'll start with on policy, which is a simpler case. And again, just like last lecture, we're going to follow the format of starting with Monte Carlo control before we move on to temporal difference learning to get more efficient, lower variance techniques. So how are we going to do that? Well, last lecture, we basically built up the toolkit that we're going to need. Last lecture, we saw how to do model-free prediction, how to evaluate a given policy. If you drop your robot into a given MDP and you ask it how much reward will it get if it follows a particular behavior, last time we saw how to do that using Monte Carlo evaluation and temporal difference learning. And that just helped us to estimate the value function of some unknown MDP. And now that basic toolkit is what we're going to use to now do control methods, where we want to not just estimate the value function, but actually optimize it, find V star, find Q star, find the best possible behavior, find the most reward you can extract from this MDP. But we're going to use the same tools, and we're just going to iterate them and essentially use what we had before kind of as an inner loop for getting to the best possible behavior. So just to get you back in the flavor, I know we've had a week off, reading week, so I think it's helpful just to get a reminder of why this is interesting. You know, why should we care? Why should we care about this particular flavor? Why this problem of unknown MDP reinforcement learning? And the answer is that in most interesting problems, and I put up just a few interesting problems here that you know, all fall under this umbrella. So, you know, controlling an elevator, getting some car to park itself, trying to automatically steer some ship, or control a bioreactor, or navigate a helicopter, or do the logistics for an aeroplane, or play Robocup soccer, or control a bot in Quake, or manage a financial portfolio, or learn how to fold proteins, or figure out how to make a robot walk by itself, or to play a complicated game. All of these problems have MDPs. There are MDP descriptions of these problems. In each case, there's some complicated environment in which this problem can be described, where there are some underlying dynamics in some environment that has some state that tells you how it's going to move around in the state. But either that thing is unknown to us, we don't know what that environment is, and so we have to resort to model-free control to figure out how to do this, or the MDP might be known, but it just might be so complicated that it's actually too big to use except to sample it. And if you can only sample it, you're essentially back to the same case as model-free control, where you really, the only way you can access this model is by just trying things, trial and error, and see what happens, because you can never do even one step of integrating over some vastly complicated model. It might be too expensive. You know, the real world's an example where, you know, the underlying dynamics of the real world are extremely complicated. Even if we knew them, you wouldn't really want to work at the atomic level and, you know, integrate over the dynamics of every atom moving around. You would just take samples, see what happens, and work with that. So model-free control helps us to solve problems like these. So that's why this lecture is interesting, I hope. Okay, so we're going to look at this basic dichotomy between on-policy learning and off-policy learning. So let's just understand what that means now. So on-policy learning, I like to call it learning on the job. So it's like you've got some policy, you follow that policy, and while you're following that policy, you learn about it. So you basically it's actually a sampling experience by sampling actions from some policy pi, and at the same time you're trying to evaluate that same policy. That's what we mean by on-policy learning, that the actions that you take determine the policy that you're trying to evaluate. But that's not the only choice. We can also do off-policy learning, which you can kind of think of as looking over someone's shoulder. So you might have you know, some robot which is watching some other robot walk around, and it's trying to figure out the optimal behavior by just observing some other robot, or maybe even a human, behave. So maybe a human gives some example demonstrations, maybe some teleoperated arm, and the human says, this is how you should move this arm around. And now, just from the trajectories that have been sampled from the human behavior, we could actually do off-policy learning, and we could learn to evaluate. The robot could start to learn for itself, well, what would happen if I did something else? You know, maybe there's some better behavior, and the robot can learn about that better behavior from samples of experience drawn from, say, the human behavior. You don't have to learn about the behavior that you sample. You can learn about other behavior. That's called off-policy learning. Okay, so we'll start with a simpler case on policy learning. And the main idea that we're going to use throughout this course is the same idea that we saw a couple of lectures ago when we were doing dynamic programming. And it's the basic framework of generalized policy iteration. So just a quick refresher slide. So the main idea in policy iteration is to alternate between two different processes, where first of all we evaluate a policy, and then we improve that policy. And we have this iterative process, which I kind of sketched up on this diagram here, where you start with some value function and some policy, and every step, every time you go up, you basically evaluate your current policy to get you a new value function, and every time you go down, you act, say, greedily with respect to that value function. I should just say greedy, actually. And so this alternating process we saw when we were doing dynamic programming actually does converge on the optimal policy and the optimal value function. And it's just this cycle that can go round and round and round. And the question is, well, what can we slot in for these two processes? And what we're going to do today is we're going to vary the choices of what slots into these two pieces here, so to enable us to do model-free control, rather than in dynamic programming where everything was using full knowledge of the MDP model. So far we've only seen in the dynamic programming examples of these where our up arrows were some way to evaluate the policy, and we saw things like iterative policy evaluation, and the down arrows were things like greedy policy improvement. And now we're going to vary those two components and try other choices. So let's make a first try. Okay, let's say, we want to do the simplest case. Let's start with Monte Carlo learning. So we're doing basically Monte Carlo control. That's this section. We're in that chapter of the lectures. And so we're going to start with Monte Carlo control. Later we'll move on to TD control. Now, if we're doing Monte Carlo control, is it possible to just slip that in? Can we just swap in Monte Carlo policy evaluation instead of our dynamic programming? That would be a way to evaluate the policy. So remember, Monte Carlo evaluation is just, you just execute some trajectories and take the mean. And that's your value of your value function. So what about doing that as our process for estimating the value of the policy? What would happen if we just ran some trajectories, used those trajectories to estimate V, and then applied greedy policy improvement? Would that work? Any thoughts? Any problems with this idea? Do people understand what the suggestion is? That we can take this general policy iteration framework and plug in a model-free step for policy evaluation to just run some trajectories in the unknown environment, see how well we do, use that to estimate the value of the policy, and then iterate by improving our policy, evaluate the new policy by running some more trajectories, evaluate our new policy, act greedily with respect to that, run some more trajectories, etc. And according to our knowledge of generalized policy iteration, this has to converge on the optimal policy. So what's wrong? Can anyone think? There's actually two problems with this. Okay, good.
So if when you're running your trajectories, you follow your policy, then you're not going to explore very well.
Okay, great. So that's one of the two problems. We'll actually come to that one second. So, but the point was, which is correct, is that there's an exploration issue, which is that if you act greedily all the time, you don't guarantee that the trajectories that you're following explore the entire state space. And so it might be that there's parts of the state space which are really interesting and actually have better potential that you just never see. Okay, there's one more problem with this. Any thoughts? So that's actually the problem with the second step. Any problems with this first step, with evaluating V in this way? Yeah?
You need to run a whole load of trials to get a good measure of what the best policy would be at any given step.
Okay, so the point was that maybe it's slow to do this, that it might be, you might need a lot of episodes to actually make this work. That's true, and we'll improve on that by using temporal difference learning later. But let me move on. So the issue is that we're trying to be model-free, actually. We want to be model-free, but how can you be model-free when you're using the value function, v? If you use the state value function and you only have the state value function, and you want to act greedily with respect to the state value function, you still need a model of the MDP to figure out how to act greedily with respect to that value function. You only know the value of each state. And so if I'm in some state and I want to know, well, which action is best, I have to imagine what would happen for each possible action. I have to roll forward the dynamics one step to look at the value function of my successor state. We don't know those dynamics. We're trying to be model-free. Okay? So if you work with the state value function v, you always need a model in order to do your policy improvement, because you need to have one step of look ahead to get to your next state. So the alternative is to use Q. The alternative is to use action value functions. Action value functions enable us to do control in a model-free setting. And the reason is that we can do policy improvement in an entirely model-free way. Like if we have Q and we want to do greedy policy improvement, all we need to do is maximize over our Q values. So we've got the Q values. The Q values tells us from each state how good is it to take each different action. Now if we want to make a better policy, what do? Well, we just pick the action that maximizes our Q values. That's the best action. It's immediate. You don't need a model to roll anything forward. It's already there in the structure that we've created. So by caching the values of our actions, we would kind of reduce the burden of what we require from our model. We don't need to look at the model anymore. We don't need to roll it forward. Is that clear? Okay. So let's drop that in. So what would that look like now? So the proposal then is that we have now an algorithm which looks like this, where we start with a Q value function now, an action value function, and some policy. And every step we're going to do a Monte Carlo policy evaluation, run a bunch of episodes. At the end of those, we've got some estimate of our policy of Q pi. So we run a bunch of episodes. We take the mean from each state action pair. We look at the mean return to estimate QSA. And that tells us how good that particular state action pair is. Taking that action from that state, what was the mean return that you got? Do that for all states and actions. That gives us a new value function. We then act greedily with respect to our Q. That's immediate. We just take this argmax over our Q values. That gives us a new policy. We run that policy for a bunch of more episodes, take the mean of all our state action pairs again, and iterate. And again, this results in Q star and pi star, or does it? And the issue has already been raised by someone in the audience, which is we still have one issue, which is that we're acting greedily as our policy improvement step. And if you act greedily, you can actually get stuck. You can actually not see the states which you need in order to get a correct estimate of the value function. So we're basically estimating the value of all state action pairs by trial and error, by running episodes. But if we don't see certain states and actions, then we won't evaluate them correctly and we won't select them because we haven't seen how good they are. So that's the distinction. Now that we're running things, we're not doing these full sweeps that we were seeing in dynamic programming. We're running things by actually interacting with the environment, so we need to make sure that we continue to see everything. So here's an example to make that a bit clearer. Okay, so this is something from the academic world where you can imagine there's some situation in life where you've got two doors and you're trying to pick the best door. So in this cartoon, one of them behind that door is tenure, or one of them has tenure, and one of them is flipping burgers at McDonald's. So now we have to basically figure out by trial and error which door to go through. So let's say you get repeated trials, and let's say the outcome of these doors is actually stochastic. Okay, so you're just going to get some immediate reward. This is called a bandit problem. We'll see more examples of this in a subsequent lecture when we focus really on exploration. But it's a bandit problem. You've got two choices, door 1 or door 2. So what happens now? If you open the left door and you see a reward of 0, okay? So you get this reward of 0 for going through the left door. So now think, okay, 0 wasn't so great, maybe I'll try the right door. So you open the right door and you get a reward of +1. So if you're acting greedily, there's only one logical thing to do, which is to open the right door again. Let's say it gets a reward of +3. So now your mean, after these steps, you've seen 1 + 1 and 1 + 3. So your Monte Carlo estimate of the value of that door is now +2, the mean of those two episodes that you've seen. So +2 is clearly better than 0. So if you're acting greedily, you would pick it again. maybe you get a reward of +2 again. And now you've got a mean of 2. So you'll open it again. And then maybe your mean is just going to fluctuate a little bit around 2. Let's say you always get a reward between, say, 1 and 3. You'll keep on opening this door forever. And the problem is that actually we don't really know what the value of this door is. We've only tried it once. And so you need to carry on exploring everything to make sure that you understand the true value of all of your options. If you stop exploring certain actions, you can end up making incorrect decisions, getting stuck in some local incorrect optimum. Your beliefs can be incorrect, and you need to carry on exploring to make sure that you really understand the values correctly. Okay, so do people see how you can get stuck in this situation and just keep on misevaluating? So how do we do that? How do we make sure that we carry on? Well, there's going to be a whole lecture on this, but we're going to start with the simplest possible way to guarantee that you continue to visit all states and all actions infinitely often. And so this is the simplest idea for ensuring continual exploration. It's actually surprisingly hard to do better than this simple idea, although there are lots of much more sophisticated algorithms. And the simplest idea is what's called epsilon greedy exploration. And it's very simple. All it says is that you flip a coin. With probability epsilon, you choose a random action, completely random, a uniform random action. With probability 1 minus epsilon, you choose the greedy action. Okay? So you flip a coin. If it comes up heads, you act completely randomly to make sure you see everything. If it comes up tails, you choose the best thing that you know so far. You take your argmax over your Q values. So it's just like our greedy policy improvement, but we've softened it a little bit to make sure that with some small probability, you try all the other actions. So this might seem naive, but it has some nice properties. It guarantees that you continue to explore everything, and it guarantees that you actually improve your policy as well, as we'll see shortly. So this is just a fancy way of saying precisely that. You know, this is saying the probability is, if you flip the coin, so this epsilon over m is the probability of what happens if it comes up tails and you explore, and this 1 minus epsilon is the probability of actually if it comes up heads, then you pick the greedy thing. But you might also pick the greedy action just by random as well if this tail thing comes up, which might have a bit more probability mass on this one. But the idea is very simple. You just either take the best action or you explore at random. Okay, so one of the reasons that epsilon greedy is a nice idea is that it actually guarantees that we get a step of policy improvement. So remember, for this generalized policy iteration idea, we want to alternate between steps of improving our policy and steps of evaluating our policy. And so what we can see is that epsilon greedy actually is a policy improvement. Like you start off with one epsilon greedy policy, and now the question is, if you evaluate that policy, so you start off with pi, that's your previous epsilon greedy policy. If you evaluate that to get you v pi, the question is, can we be sure that by taking epsilon greedy step, like by acting epsilon greedily with respect to v pi, can we be sure that we've really made a better policy? And the answer is yes. So the simple proof here, which basically says that if you look at, so we're just going to do the same idea we saw in the dynamic programming lecture, where we're just going to prove this over one step, and then we're going to argue that that whole thing telescopes by unrolling it using the Bellman equation. So over one step, we can see that the value of our previous policy, of our original epsilon greedy policy, if we take one step of our new policy, so we want to show that this thing here, taking one step of our new policy, is basically better than our original policy, than the value of our original policy. So this is just saying, well, this is just an expectation. So this is our epsilon greedy policy. And we're going to say for one step, there's some probability that we're going to take each action, multiplied by the value of that action. This is just unrolling the expectation. And we can split that into the probability of taking the greedy action plus the probability of taking all other or every action. So this is what happens if you choose to explore, and this is what happens if you choose to act greedily. And now what we can say is that, well, this thing of where you choose to act greedily, if you act greedily, if you choose the max of all your Q values has to be at least as good as any weighted sum of all of your actions. Right? The max is better than any weighted sum of your actions, of your Q values. So we're going to choose one particular weighting that sums to 1 here. And we're just going to say that the max has to be better than that weighted sum of your Q values. And now you can just collect terms together, and we see that we've got 1 minus epsilon on 1 minus epsilon. So this term over here now just cancels with this term over here, and you're just left with an expectation over your Q values, which is your original value function. Okay, you can look at this afterwards, but the main thing I want you to take away is this idea that epsilon greedy, very simple idea, but it really does guarantee that you're making progress. So you really do make progress. You start off with some epsilon greedy policy, you evaluate it, you make a new epsilon greedy policy, and it's definitely better than what you started with, or at least as good as what you started with. Okay, and then for the final, to telescope it, refer back to the dynamic programming lecture that explained how this telescoping argument works. It's the same idea. Okay, so that's the one slide of math. Go on, question.
Well, this proof you've just shown us doesn't really tell us anything about the rate of being exploration, really. Because I think if you did like completely greedy policy, then that would actually, you prove that's better than anything, but you're not taking into account you actually want to explore the environment more.
So I'm not sure I understand the question. So is the question, can we say anything about how frequently you need to, like how epsilon affects?
Is it telling us anything about in our real problem, when we execute our real problem, how much we should be exploring?
No, this doesn't really in itself tell us anything about how rapidly we should be exploring. So, but in general, we'll see a little bit about that in a second, that you need to choose a schedule for your epsilon, and you need to make sure that that decays to 0 roughly, but we'll see. So let's see how to plug that in now. So we've got two ideas now. We started with this generalized policy iteration framework, and we've changed each of these steps now. We have these two processes. So for the policy evaluation, we're now plugging in Monte Carlo as our way to evaluate our policies using Q, using the action values. So we've got this one process here where we just run some episodes using our current policy. We estimate the value of all states, all actions from all states, just from what we've seen. So for every state action pair, we look at the mean return we've seen. That's our evaluation procedure. As someone's pointed out, that might be a little bit inefficient, and we'll see how to improve that shortly. But now, we've also changed our policy improvement procedure to use this epsilon greedy policy improvement, where we basically have this softening of the greedy idea. So every time we go down, we're not getting to the completely greedy policy, we've got a little bit of exploration left. And so the policy is always stochastic along here now, and that stochasticity in the policy ensures that we, at some rate at least, explore everything in the environment. Now, as pointed out by the question there, the rate at which you actually see, it might be very, very slow still. There might be some states that are way off down some strange trajectory, and you have to explore and explore again and explore again to be able to even see those states. So this doesn't actually give you very strong guarantees of how long it takes to explore all of those states. It just says asymptotically, at least, this thing now really will find the optimal policy at the end. It should say Q star. This should all be Q rather than V. Okay, so let's try and make this a little bit more efficient. So the first thing to note is, again, we saw in the dynamic programming lecture, that it's not necessary in these kind of policy iteration frameworks, it's not necessary to go all the way to the top of this line every time. It's not necessary to fully evaluate your policy. Sometimes you can just spend a few steps to evaluate your policy, and you've already got enough information there to guide you to a much better policy without wasting many, many more iterations on gathering more information. So what would that look like in the context of Monte Carlo? Well, let's take it to its extreme and say, why not do this every single episode? So we're going to run one episode, going to make the robot do one episode, collect all the steps along that episode, update the Q values just for those steps, so we basically get one new return. And so for every state and action that we've taken along that return, we're going to update the mean value just of those visited states and tried actions along that episode. So one episode, one sequence of updates to our returns, and then improve our policy straight away. Why wait? Why wait to get more episodes of information when you can already improve the policy? So the idea is, always to act greedily with respect to the freshest, most recent estimate of the value function. Like if after one episode you can already update the value function to something slightly better, then why continue using your old estimate of the value function to generate behavior? You may as well use your new updated value estimates to continue generating behavior. And so we changed the sort of the time, the rate at which we operate in this diagram becomes more frequent. The frequency increases. We don't go as high up. We just run one episode, and then we immediately improve the policy. One episode, immediately improve the policy. Run one more episode, improve the policy. Is that clear? Okay. So this question's already come up, and it's a natural question, which is, how can we really guarantee that we find the best possible policy? Like, what we really desire is pi star. We really want to know the best possible behavior in this environment. So to do that, we have to kind of balance two different things. We need to make sure that we continue exploring to make sure that we don't exclude things which are better, but we also want to make sure that asymptotically that we get to a policy where we're not exploring at all anymore, because we want the best possible policy, and the best possible policy will not include this random behavior. That is extremely unlikely to be optimal. So how do we balance those two factors? And so one idea for balancing those two factors is called this GLEE idea, greedy in the limit with infinite exploration. And the idea of GLEE is basically to come up with any schedule, if you like, for exploration, such that two conditions are met. The first condition is that you continue to explore everything, that you basically make sure that all states and all actions are visited infinitely often. So that's like guaranteeing that you just that you never miss out on anything. That just to make sure that every little part of the state space will be seen, every action from every part of the state space will be tried. So, for example, epsilon greedy has that property that eventually, if you behave randomly and you try all possible actions, then every reachable state in the state space and every action from those reachable states will be tried. Okay. And the second property is that we want to make sure that the policy eventually becomes greedy. And it needs to become greedy because we need this thing to satisfy the Bellman equation. And the Bellman equation is basically, the Bellman optimality equation basically requires a max in there, not just some soft thing. And we want to make sure that eventually we're acting greedily with respect to Q, and we're really taking the max, or the argmax of our Q values, eventually. And so one way to achieve this, by no means the best way, but certainly one simple idea, is to choose an epsilon greedy policy and just decay epsilon slowly towards zero. So for example, if you choose a hyperbolic schedule, so each episode, you basically, on the kth episode, you set your epsilon to say 1 over k, that satisfies these two properties. That you will see everything infinitely often, but asymptotically you become closer and closer to optimal. Closer and closer to the greedy policy. Okay, so that's one way to balance things. So what does that look like in practice? Well, we can make an algorithm now. Let's call this GLEE Monte Carlo control. So this algorithm, basically we start off by sampling episodes. So again, we've just got our robot, we throw it down, we run one episode, that generates a trajectory of states, actions, rewards, state, action, reward, until we get to some terminal state. We sample that from our current policy, pi, and then for each state and action that I visited, so I got to this state and I picked this particular action, for each of those states and actions, we update our action value. And the way that we do that is just by counting how many times we've seen that state-action pair and doing an incremental update to the mean. So this is just our incremental update to the mean, which says that if we consider that particular state-action pair, this one over here, this state and this action, how many times have I tried that? Well, let's just adjust our previous mean, which was this. We're going to update a little bit in the direction of the return that we just got. And the amount that we have to adjust it to get a correct mean estimate is this 1 over n. Now, what's interesting about this is we're not taking a mean in the way that you think of it's not like a statistical mean over some IID quantity now. that the policy is actually changing over time. We're iterating over our policy, we're improving our policy, but we're basically taking returns from better and better policies into account. So as we improve our policy, we're gathering more and more statistics, our policy starts to get better, and we collect all of those statistics together to get us one overall mean of how good it is. And the GLE property basically ensures that over time, that these statistics that we're collecting really sort of converge on getting the mean return for that these policies sort of get more and more like the greedy policy. And so we basically find out more and more information about the policy that we really care about, that the past kind of gets dominated eventually by these new policies. And so what we're going to do now is we're going to iterate over this whole process. So we're going to sample the kth episode in this way, update our Q values, and then improve our policy. So this was the policy evaluation step. Now the policy improvement step just looks like this, where we can, for example, set epsilon to its new value, 1 over k, and now we're just going to act epsilon greedily with respect to these new Q values. And those Q values are going to be the same everywhere, apart from the states and actions that I just visited. So we only update those Q values along one trajectory, but that's already enough to change the behavior that we actually see there. So in practice, if you're actually writing this, you don't need to explicitly store